Hello students, welcome back to Math 332 Linear Algebra. In this section, we are going to look at a concept called change of basis. So the central problems for these presentations is this. Given a finite dimensional vector space, we can find many different bases for that space. And let's say we have basis B1 and we have basis B2. And we also have a vector from that vector space so that we can write the coordinates of that vectors relative to basis B1. And we can also write the coordinates for the same vectors relative to basis B2. So the question is, what's the relationship? What is the connections between that two coordinates? And that is the thing we want to investigate in this video. All right, so without further ado, let's get right to it. All right, let's begin by looking at the objective for this section. So at the end of this video, you should be able to find the transition matrix and know how to change the coordinate of the vectors using this transition matrix. All right. So as mentioned, the central problem for this sections is you have a vector v, and which is coming from this finite dimensional vector space. And for this vector space, you have basis b and you have another basis b prime. So if you write the coordinates of this vector v relative to b, and you also write the coordinate of this vector v relative to the basis b prime, how are the coordinate vectors, how are these two coordinate vectors are related, right? So that's the central problems that we're going to investigate in this video. And the relationship between these two coordinate vectors is actually given by something that equation that looks like this. So let's start by looking at this example, okay? So you have a vector space V, suppose they are dimension 2, and you have these two set of bases. So because the vector space is of dimension 2, so there are two vectors inside this basis B, and there are two vectors inside this basis B prime. So take a vectors from that vector space. Obviously, you can write the coordinates of these vectors relative to B prime. You can also write the coordinates of the same vectors relative to basis B. And I'm claiming, we're going to show that later, but I'm claiming right now that these two coordinates vectors are related in this manner. Okay, here, this one right here is a matrix. This matrix here consists of the first column of this matrix is actually the coordinate of this vector u1 relative to basis b prime. The second column here is this vectors, okay, u2, the coordinates, not the vector, but the coordinates of that vectors, u2 relative to basis b prime. So you write as the second column here. So we can call this matrix here, we actually call this matrix here as a transitions matrix from basis b to b prime, and the notation for it is this. So this equation here can also be expressed like this. All right, so this kind of notations, we create this kind of notations is not out of thin air. This is kind of like suggestive that if you put the coordinate, right, which is from basis b, it will transitions to b prime, so you'll get this coordinate relative to basis b primes. That's why the arrow is pointing this way. All right, so think of it kind of like a functions. So the input going here, so you have a coordinates of a vectors relative to basis b, and then this matrix is going to transfer it to a coordinates relative to basis b primes. Hence, this is the notations. All right, and let me point it out one more time. How do you construct this matrix? This transition matrix is constructed this way. First, you write the vectors that is from the starting basis. So this is what we call the starting basis, right? We start from here. This is where we're going to end, right? So you write the vectors u1, u2, but not the vectors, but the coordinate of the vectors, but it's the vectors that is from here, but you write the coordinates, but the coordinate relative to this basis b prime. So you pick up these two vectors, okay? You pick up these two vectors, take the vectors, okay? Find the coordinates relative to basis b prime. Take these vectors, all right? Find the coordinate relative to basis b prime and write as the first column and the second column of this matrix. So this matrix is constructed like this, all right? Don't get too boxed down by the notation b and b prime, because all this thing here, you can change the notation pretty easily. So you can start thinking like, this is the starting basis, so we take the vector from the starting basis, write the coordinates of the vectors from the starting basis relative to the ending basis. So you can call this a starting basis, all right, and this is the ending basis. Some people also call it, this is a old basis, this is a new basis. There are many different ways to call this. And let's start by looking at this example, okay? So as you can see, I purposely rewrite this basis. I didn't use b and b prime anymore. I am still working on the vector space of dimension 2. We can tell that because there are two vectors right here. All right, so we have this basis B and basis C. Okay, so these are two vectors, two bases for R2. All right, so U1 is like this, U2 is like this, V1 is like this, V2 is like this. As you can see, none of them are standard bases, but those are bases for R2. All right, so how do we construct this transition matrix from B to C? And also, given a vector x with the coordinates relative to basis B is 1, 3, what is the coordinates of this vector x relative to this basis C? All right, so let's look at how we find the transition matrix. Okay, so transition matrix P, B to C. So what do we need to do? Well, we need to take a vectors, some vectors, and find a coordinate and place this as the first column right here, and then do the same thing on the second column. So what should go into the first column? So this is our starting basis. So this is our starting basis. So we're going to write U1, but not the U1 vectors, but instead the coordinates of this U1 relative to basis C. All right, so starting basis B here has two vectors. They are U1 and U2. We are not writing U1 and U2. We are writing the coordinates of U1, U2 relative to the ending basis right here. So this is coordinate. These are going to be coordinates of the U1 vectors relative to basis C. And this is going to be the coordinates of the U2 vectors relative to basis C. All right, so this is how you write down your transition matrix. So how do you find the coordinates of U1 relative to basis C, and how do you find the coordinate of U2 relative to basis C? So the definitions for coordinates, right? So now we wanted to write as the coordinates of the basis C. So we will have to basically write U1 equal to this, right? And the coordinates for the U1 vectors coordinates relative to basis C is going to be these two numbers K1 and K2. And if you write U2 as a linear combination of V1 and V2. V1 and V2 are the basis vector from the basis C. So this coefficient here, K3 and K4, these two coefficients, these are the coordinates of this vectors U2 by definitions, all right? So what we need to do is to find all this K1, K2, K3, K4. So this is solving system of equations. This is also solving system of equations. So as you can see, this system of equations can be written as a augmented matrix like this, which can row reduce to this. Same thing here, which can row reduce to this. So we got our K1, K2 as -3 and 2, and K3, K4 is 3 and -1. And these are by definitions the coordinates of the U1 vectors relative to basis C. And this is by definition the coordinates of the U2 vectors relative by basis C. So these two vectors will go in right here to form the transition matrix from B to C. So we have finding coordinates. We are finding coordinates of the vector U1 relative to basis C and coordinates of vectors U2 relative to basis C. These are the coordinates. These are the coordinates. So our transition matrix will be this. Our transition matrix from B to C will be given by this matrix. Okay? Now, so how do we use this transition matrix? So now we have vectors x. We don't know what vector x is, but we do know the coordinates of this vector x relative to basis C. Okay, this is what we want to find. The things that we have is the coordinates for this vectors x relative to basis B. So this is what we have. This is 1, 3, and we are going to find what is this coordinate. So how do we do that? Well, so remember this will be given by P, B to C, all right, and then X, all right, B. So the way we look at this is that look at it as if like a function. You take a coordinates relative to basis B. If you multiply through this transition matrix will transition, so to speak, the coordinates from B to C. So you will get the coordinates for this vector x relative to C. So what happened is you just multiply these two matrices together and you get 6, -1. That will be the coordinates of this vector x relative to the basis C. So that's how we use the transition vectors, right? The transition matrix. Okay. So how does this work? Okay, so how is it that if you are in a vector space of dimension 2, I'm giving this as an example, I'm not showing this as general proof, but let's say you are in a vector space of dimension 2 and you have these two bases, b and b prime. Their basis vector here is u1 and u2, u1 prime and u2 prime. How do we know that the way that we construct this relationship works, right? How do we know this works? Okay, how do we know that this coordinates is given by the product of these two matrices, where this matrix here, which called the transition matrix, is given by this. Okay, so let's look at the proof. It's pretty easy to understand the proof. So we start with the so-called start basis, sometimes also referred to the O basis. So B prime here is our end basis, our ending basis, and this is also sometimes referred to as our new basis. So we want to find a transition matrix from our O basis to the new basis. Okay, so what we're going to do is we are going to write, okay, U1, right? Okay, these vectors, we're going to write the coordinate relative to basis B prime. Let's call them AB. We are going to write the coordinates of U2 relative to basis B prime. Okay, so let's call that coordinate CD. So if you do that, by definition of coordinates, right, if this is AB, this is CD, so U1 by definition of coordinates will be A of U1 prime, okay, and B of U2 prime, and we also have this one right here. So this is nothing but a definition. It follows from the definition of coordinates. If you call this coordinates AB, if you call this coordinates CD, this is what it means to have these two coordinates. All right. So now, so this is our starting point, right? And then you take a vectors, any vectors, a fixed vector from this vector space V. So because your vector space V has basis, okay, basis vector u1, u2. So we can definitely write as k1 of this u1 and k2 of this u2, because being a basis vector, it spans the space. So if you take a vector v, we can write it like this. So now we are going to rewrite our u1 by introducing u1 as a linear combination of u1 prime and u2 prime. So we are going to write our u1 using this equation. I'm going to write our u2 using this equation. That's the reason why you see this. All right, so K1, K2 are numbers, right? All those A, B, C, D, they're also numbers. So you can regroup all these numbers. Okay, you multiply and redistribute. So these are all numbers now. So these are all numbers. So you have a whole bunch of scalar multiply U1 prime. You have a whole bunch of scalar multiply U2 prime. So now if you take a look, if you can write V as a linear combination of U1 prime and U2 prime, can you tell me what are these scalar? What are the meaning of this scalar? The meaning of this scalar, okay, if you remember, that's the coordinates of this vector v relative to which basis? Relative to the basis b prime, okay? Because you managed to write down the linear combination of this vector v using the vectors u1 prime and u2 prime. So by the definition, the scalar here is the coordinate. All right, so our v, okay, our vector v has coordinates relative to basis b prime as, what's the coordinates? What are the coordinates? The coordinate is k1a plus k2c and then k1b plus k2d. That's the coordinate. So the v, vector v, okay, the coordinates relative to basis b prime is this. And this is actually the products of these two matrices. And what is this? Wow. What is this? This is the coordinates of u1 relative to b prime. This is the coordinate of u2 relative to b prime. So as you can see, the way we write this, k1, k2. What is k1, k2, by the way? K1, k2 is the coordinates of v relative to basis b. So you can see that this one right here is this one right here is this, and this one here is actually this, right? And this one here is actually this. So that is how we get this relationship, right? The AB here is actually the coordinate here, the CD here, right? Let's take a look one more time. Let's get rid of all this. AB is the coordinate here. CD is the coordinate here, right? Okay, K1, K2, K1, K2. That's the coordinates for vector V relative to basis B, right? Okay, and if you put them together, you will be able to see that that's how we get this transition matrix, and that's how the transition matrix looks like this. Okay, so let's look at another facts before we move to the next example. So suppose you have bases B and B prime. These are bases for a vector space V. So let's take a vector again from that vector space, and let's write the coordinates, right? The coordinates of this vectors relative to B prime. And we know from before, this coordinates is related to this coordinate, exactly like this, through this transition matrix. And let's write this vector V, same vector V right here, but let's write the coordinate, this time relative to basis B. And we also know from before that this coordinate right here and these coordinates are related in this manner, where the transition matrix here is from B primes to B. So let's look at it one more time. So this is transition matrix from B to B prime. So if you put a coordinates relative to B, it will give you the coordinates relative to B prime, because this is transition matrix from B to B prime. Okay, now this one right here is a transition matrix from B primes to B. So if you take the coordinates that is relative to B prime, it will give you the coordinates relative to B, right? That's how the transition matrix notation actually means. So now if you look at this vectors, right? This vectors V, and you look at the coordinates relative to basis B. So we know the relationship is given by this. And now this one right here has this relationship. So let's substitute. V, the coordinates of V relative to B prime. Let's substitute inside here. And then these are matrices, right? So these are all matrices. So associative rule, matrix multiplication is associative. So you look at this matrix, multiply this matrix right here, and then multiply this matrix equal to this. So this matrix right here and this matrix right here is the same. So these two matrices, okay, these two column vectors, okay, are related by this relationship. So we know immediately that these two products, the product of these two transition matrix, is the identity matrix. All right, so this one right here has to be an identity matrix so that this relationship will hold, right? So once you get to this, all right, you will know immediately that these two transition matrices are invertible. So transition matrix are invertible because the products is the identity matrix. So this transition matrix is the inverse of this, right? And this inverse is this transition matrix. All right, so now we have figured it out that the relationship between transition matrix from B to B prime and the relationship between the transition matrix from B primes to B, they are inverse of each other. Okay, so these two transition matrices are inverse of each other. Why is this good? Because we can actually apply this to solve some problems. Okay, let's look at this example right here. So as you can see, we're no longer in R2. We are actually in the vector space of polynomial of degree at most 2. So this is the standard basis. Okay, 1x and x squared is the standard basis for P2. This is not the standard basis for P2, but this is actually a basis. All right, so we have justified that from before. So the question here is, find this transition matrix from B to C and find this transition matrix from C to B. And then use a suitable transition matrix, find the coordinates of this polynomial relative to basis C. So this is a polynomial. This is the coordinate. So remember, coordinates of any vectors is always column vectors in Rn. So it doesn't really matter you are working in polynomial space. If you're working of spaces consist of matrices, the vectors are different. The vectors are polynomial, the vectors are like matrices, but the coordinates is always a column vectors in Rn. Okay, so the first thing is that if you look at this carefully, you will see that actually between these two transition matrix, this transition matrix right here is easiest to compute. This transition matrix right here is very easy to compute. Why is that so? Because in order to compute this transition matrix, what should we do? Well, we will have to take this vectors right here, 1 plus x, right? 1 plus x, and write the coordinates, right? This vectors 1 plus x, not the vector itself, but the coordinates relative to basis B, and put it right here. All right, and then the second column here is the vectors, x squared, not the vectors, but the coordinates relative to b, and put it right here. And then the third columns, you put the coordinates of this vectors, right, relative to basis b. But your basis b is the standard basis, right? So if your basis b is the standard basis, you can actually see that this coordinates is nothing but 1, 1, 0, and this coordinate is 0, 1, 1, and this coordinate is 1, 0, 1. You can see that very easily because your basis b is your standard basis. Okay, the other directions is not so easy. I mean, we can still do it, but it's not so easy to compute C to B, B to C. All right, why is that so? Because to do B to C, we will have to take vector B, which is 1, and write it as the coordinates relative to basis C. So this one right here, how do you write 1 equals to something, 1 plus x plus something, x plus x squared, right, plus something, 1 plus x squared, and we have to figure out what is that coefficient right here. So this is not so obvious, but it is obvious if the standard basis is involved. And right here, if the standard basis is involved, if these are all standard basis, it is pretty easy to see that 1 plus x is obviously 1 of 1 plus 1 of x plus 0 of x squared. So you will have the coordinate as 1, 1, 0. So that's the reason why this transition matrix is easier to compute. We don't really have to worry about the other transition matrix because we know the relationship between these two transition matrix. So one are inverse of they are inverse of each other. Therefore, if you want to find B to C, that's the inverse of this, and we can compute that pretty easily. Therefore, if you have to find the coordinates of the polynomial px right here relative to basis C, so you know that this is actually what we need to have, right? So this is the proper transition matrix. If this is the information that we have this right here, 1, 2, -1 pretty easily using standard basis. So then the coordinates with this polynomial relative to basis C will be computed this way. Okay, so one last thing is this question right here. So as you can see, we are no longer in Rn. We are also no longer in P2. We are actually on a vector subspace of M2 by 2. This is a vector subspace of M2 by 2. So you have these two bases. This is basis B and this is basis C. Your job is to find this transition matrix and also the coordinates of the vector V relative to C if you know that that vectors V has the coordinates relative to B like this. Okay? All right, I will give you a couple of minutes to work on the problem, and you can pause the video, and when you are ready, you can restart the video and I will come back and we can look at the solution together. All right, welcome back. So in order to find the transition matrix from B to C, all right, what we need is we need to take the starting vectors B1 and compute this coordinate relative to basis C. All right, find the coordinates, put it right here. Okay, so take B2, this is coming from here. Take the vector V2, this is a vector V2, but not the vector itself. What we want is the coordinate relative to basis C. And we have the coordinates of the vectors B3 relative to basis C. So the transition matrix from B to C is going to be given by this. So we need to find the coordinate of this vectors relative to basis C. So that means we will have to write B1, okay, and then solve for the K1, K2, K3. All right, take a look. This is the C1 here, C2 here, and C3 here. Okay, so we have to take B1 and solve for the K1, K2, and K3. So that K1, K2, and K3 will go right here. Okay, so if you put B2, right, this B2, all right, solve for K1, K2, and K3, that coordinates will go right here. And if you substitute this with B3, this B3, so the K1, K2, K3 is the coordinate, we're going right here. That's the definition of coordinate. So basically, you will have to solve the system. So I don't want to call them B1, B2, B3 first. I'm just going to write them generically as A, B, and C. So this gives you K1, K2, K3 equals to A. This is how you get this first equation. And you can also get the second equation doing the same thing. You get that equation getting the same thing. So we want to find the K1, K2, and K3 with the ABC here as your 1, 1, 1. That is the B1. I need to solve this system. I also need to solve this system one more time, but this time is 0, 2, 2. So I have to do 0, 2, 2. That's our B1. That's our B2. And then we have to do one more time, one last time with this 0, 0, 3. So we have to do 0, 0, 3. That is B3. And we want to find the K1, K2, K3 associated with this, and then do it one more time with this, do it one more time with this. So we have to solve this linear system 3 times, actually. We have to solve this linear system 3 times. So instead of solving that 3 times, you can see the coefficient matrix is always the same. So one thing we can do, a shortcut, so to speak, is to put your ABC as 1, 1, 1 right here, and then put your ABC as 0, 2, 2 right here, because they have the same coefficient matrix anyway. And then you put 0, 0, 3 right here, and then row reduce this matrix, okay, all the way to here. That means that we don't have to do this operation here 3 times. We just do it 1 time using the calculator or using the link that I sent you. So what we have is that this is the K1, K2, and K3 for the B1. That is to say that this column here is the coordinate. This column here is actually the coordinate of the matrix B1 relative to C. This one right here is the coordinates of B2 relative to C. This one right here is the coordinates of B3 relative to C. This one looks familiar because this is exactly what we want. This is exactly what we want. So it turns out that this matrix that you obtained right here, is exactly the transition matrix that we want to find. Okay, so this is a shortcut. Sometimes we can do that. Sometimes if you need to solve a system of equations multiple times with different A, B, and C, but if the coefficient matrix is always the same, you can put them like that so that you can see that this one gives you the answer for that system, this one gives you the answer for that system, and then this one gives you the answer for the third system. Okay, so let me say it again. I hope you can see it. This one is a solution for the first system. This one is a solution for the second system. This one is a solution for the third system. Okay, all right. It's not very difficult to see that. Okay, so you will be able to see that. Turns out that if you do it this way, we immediately get our matrix right here. Our transition matrix is right here. So once we have that, we know that the coordinates of these vectors and the coordinate of these vectors relative to bases C and B are related like this. And since we already have this is given. So look at the questions right here. This is given, right? So now you will be able to see that multiply it with this matrix. Okay, we'll get the coordinates of that vector V, right, relative to C. And all right, this concludes our presentation for this section. In the next video, we are going to look at the row space, the null space, and the column space of a matrix A. Those vector spaces are very important because they are able to provide information on the existence and uniqueness of the solution for the linear system AX equals to B. In particular, the column space is going to be able to tell us whether the solutions of the AX equals to B exists or not. And suppose the linear system is consistent, the null space of A is going to be able to tell us whether we have unique solutions or we have infinitely many solutions. All right, so we're going to investigate all those vector spaces in the next video, and I will see you then.